Hello, everyone. Hopefully, you guys are doing well. Today, I want to take a break from Blender stuff and go more into the Houdini side of things because I've been using Houdini for about a year and a half and I haven't made any actual content on it. And I've been writing a lot of simulations and stuff for terrain, and I figured I'd sort of show you guys, I guess, a little bit of like how that can be done. Uh, so all of this terrain was generated in Houdini using Houdini's OpenCL nodes. You can see the kernel here is OpenCL. And OpenCL is one of the most handy features that side effects implemented because you can write directly onto the GPU. And it's also a little bit more flexible when it comes to like fine grain tuning and stuff than Vex, which is Houdini's sort of Houdini's like scripting language that you can use. Houdini has a couple languages that it supports. It's weird. Um, yeah, so this tutorial we're going to be making these little flow lines. These are pretty cool. You can change certain aspects about them, like like friction and stuff, and how many of them. It's fun. It's going to be fun. I'm quite excited to get started on this. This does require a bit of Houdini knowledge and preferably some coding experience in the past, but it's pretty light. This is only about 50 lines of code. You can see it's only 56 here, and it's just one OpenCL node. So I trust it won't be too unapproachable, too intimidating for a lot of people. And I'll try to do my best to break it down, although I'm not always the best at explaining it. Um, so I think that's about it. Uh, yeah, I appreciate you tuning in. Hopefully you get something new. Hopefully you learn something new about this. I personally find it extremely interesting, so hopefully you do too. Let's get started. All right. Um, so Houdini has OpenCL nodes. These nodes are where you write the OpenCL kernels, which is essentially just the program that's running on the GPU. And that's written in this kernel code box. Houdini 20, which is what I'm using, Houdini 20.5 to be specific, gave a bit of an uplift to the OpenCL nodes. So you'll see if you're using Houdini 19.5 or below, it's just going to be one input and one output. And you'll also probably notice that the syntax here is a little bit different. They added this at binding feature, which allows you to more. It makes it a little bit more similar to Vex in some ways, but I'm not really familiar with all the intricacies of it. So I'm going to use the more legacy way of doing this, which is if you look in here, I have to unlock this, which is instead of like using the at kernel thing, I'm just using a kernel function that has a bunch of inputs and stuff. This is the way I'm familiar with it. It's probably not as efficient now, but I don't really want to learn something new just for the sake of a tutorial. Um, so we're going to uncheck this. And I'm going to delete this. So our first objective here is just to make it so that's not erroring out. So to do that, our first thing that we're going to do is we're going to change this first writable attribute to first writable volume. And then we're going to add in a binding here. So that just clicking the plus here on this multi-parm. And we're going to call this type because we want to reference the volume that is called height, which is essentially just the height map that is being rendered here. So height, then we change this to volume and name this height. So it's important to know this volume, this is actually reading the volume named height from the this first input here. This parameter name can be anything, it can be like H or whatever. I'm going to call it height just for clarity. But this can be whatever you want. It's not actually connected to this volume. It's just the parameter name. uncheck force alignment. So you could, this is basically just to keep all the extra, like if you're binding in multiple volumes, if they have different resolutions and sizes, it's going to create an error, and it can be helpful. I don't think it's explicitly necessary, but uh, it is definitely helpful and allows you to do a little bit less. What's the word I'm looking for? Makes everything a little bit cleaner. Let's just do that. So these are the things that we want to import. So we want to get the volume resolution and the voxel size, and then we want to check this writable box here. And then if we go to this generated code, we can generate the kernel. We can copy this function and paste it into here. And it's not erroring out, which is great. So this is fine and dandy. Let's first start by how do we actually like read from and write to this data. So we have these variables gidx, gidy, gidz, and then this idx. These are basically the coordinates of the point of the voxel in local space, right? So this is the x coordinate, y coordinate, z coordinate. Instead of so in OpenCL, the volumes are, well, pretty much every data set is an array. And it's a pretty large array, right? If it has to store all the values at every point here. So this IDX, this is the index in that array. So if I do height, so I'm referencing the height volume and brackets inside here, IDX. This is reading the value of height at the index IDX. And we're going to do plus equals 1. This is just to do a quick test to show you how you can modify this a little bit. So you saw it jumped up a little bit. And then you can change this iteration here. This is going to be how many times it executes this code. So if I change this up to 10, you can see it's raising and lowering. Oh man, what's with my voice today? It's voice cracking all over. So that's a very basic function. One of the things I want to sort of illustrate here how IDX works and how like this index is sort of distributed across the terrain. It kind of goes in like stripes. So it's going to go from like, I'm not sure if it's specifically oriented like this, but it's like IDX 0 starts at here, and then it goes up by 1 for every voxel that it goes this way. Then it loops back and does the same, and it loops back and does the same, does the same, does the same. You don't usually have to contend with this too much because this function kind of naturally just computes it for you. But it can be useful to know, and we are going to be leveraging that fact a little bit. The first thing I want to do though is I want to just clean this up. I don't like having this height prefix on all of these. I think it's a bit just unnecessary. Creates more typing. So I'm going to delete this on all of these. And then for this voxel size one, I'm going to replace this with D. So it's just dx, dy, and dz. And we have to naturally update this as well. Just removing the height. And another thing is that our height field is, for all intents and purposes, 2D. If we open up this, we can see it's 1024 by 1024 by 1. right? It's not 1024 by 1024 by 200, right? So we don't need this third axis. So we don't actually need GIDZ in any of these because GIDZ is always going to be 0 because it's just 2 dimensions. So we can see that it hasn't changed. Unfortunately, we can't just remove one of these because it's just kind of implicit in the volume definition. Whatever, the volume importing stuff. But it's just a few extra lines of code that doesn't really do anything. So yeah, we must make do. Anyways, let's grab in, or let's import in the mask field as well, because right now we just have the height. So I'm going to copy this and change this to mask. And then I need a comma after this height. And if I click, it's going to error out. If you've been paying attention, you probably know why. It's because we need to add in another OpenCL parameter for the mask. And change this to volume. This time we can keep force alignment on. All this does is it forces the dimensions of this to align to the dimensions of the first volume. Here's the description you can read. Check writable, and then we're gonna write mask in here. If you're unfamiliar with Houdini height fields, the mask is a basically it's a separate volume from the height field that just by default can highlight certain features. So mask IDX equals like 0.5. And it's going to turn the terrain like pinkish red. Right. It's a very good way of visualizing things. And we're going to be using this for the, you can see that's what we're writing to here for these flow lines. Just back to the IDX stuff. I said I was going to help visualize it, and I think that it is definitely necessary. So I'm going to just say this mask IDX is going to equal, we're going to cast this to a float IDX over, let's say 100,000. And we can see it's creating this sort of gradient, right? If I change this down to like 1,000, or even better, if I do one of the resolutions, so res X. Actually, let's just do 2,000. I'll get into that in a second, why it's all red there. So you can see this single row of voxels starts off at like this wider value, so this mask isn't quite 1. But as we move over, it gets darker and darker, deeper and deeper red until it's pretty much exactly 1 this end. So you can see how that IDX is getting is changing as it goes through the rows, and then it's changing at a more like drastic degree over the course of the entire terrain, which is why it's giving us this gradient. It's like slowly growing, like it's going whoosh, 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 until it gets over to the end. Pretty cool, actually. But it is kind of a different way of interacting with the height field than you might expect if you are only used to like VOPs or VEX. So I'm going to put an if statement here. Well, actually, let's first kind of discuss how we actually want to implement the flow lines here. I think I can sort of give a demo. If I turn the strength up here, you can pretty clearly see what's happening. It's a bunch of these particles that are being just rolled down a hill, and then they sort of accumulate. If I turn this down quite a bit. It's a little bit easier to see sometimes. Right, so it's a bunch of these particles. So the first thing we need to do is we need to actually generate these particles, and then next we need to make them move, ideally down these slopes, and then we need to render them out onto the height field, and we're going to be using the mask field to do that, right? So that it colors them in these particle trails in red. And then from there we can add a little bit more like control parameters like this friction and stuff, which is pretty fun. All these guys. So let's get started with scattering these particles. So it's not entirely obvious how to actually do that, especially if you're coming from like a VOPS or a VEX background, because how do you like scatter points using only volumes? Like that's kind of a weird thing to think about. Oh well, I just did something weird there. But luckily for all of us, there's a pretty easy solution. It just requires a bit of like reframing how you think. And using this IDX value is actually really handy here. So one of the things we can do, let's say we want to set mask equal to 1, right? It becomes all red as predicted. But if I put an if statement here, if IDX is greater than, or sorry, less than, let's say 10,000. And then I'm going to encase this in here. Boom, suddenly all of these values of IDX, or voxels that have a value of IDX that's less than 10,000 are getting highlighted. So now we have 10,000 precise voxels highlighted. I'm going to refactor this to be a little bit more clean. That way we don't have to do everything after this inside of this if statement. So I'm going to bring this out. I'm going to change this to greater than, and then inside of here I'm going to put this return statement, return nothing. And this will basically make it so that if IDX is greater than 1000, I'm going to return this blank value, and then nothing after this return is going to be executed. So we get the fundamentally same thing. So this is really cool. Now we have 10,000 individual points that we are running over. So now we need to use these points to or now we need to like actually scatter points, which is definitely going to be it's still not intuitive how we do that. I'm just gonna put it that way. So one of the unique things about OpenCL is that you can use this, you don't have to write just to IDX. IDX is the index of the voxel, but you can say I want to write to the voxel of index IDX plus 100,000. And now suddenly something like this happens. It's like, whoa, what's that? Why did it just shift over? That's because we're writing to the voxels that have an index of like 100,000 plus IDX. I'm kind of being redundant here. Hopefully you can kind of intuit why that happens. It's very hard to create explanations for things on the fly. Anyways, this might illustrate a little bit easier why it's possible to scatter points. But in order to do that, we have a smaller step that we need to do, which is add in like a sort of random function. Now, OpenCL, yeah, so the random function is just to say, I want to take this voxel at these coordinates and I want to shoot it over to a random point on this plane. That's why we need a random function. So, luckily for us, Uh, I have one that I've been using for a little while. OpenCL doesn't come with like a white noise texture or like any of those random textures, so I kind of just built this one myself, uh, just because it's quite necessary. They do have some simplex noise that you can import. Like in this options, you can say include simplex noise data, but I'm not sure how to do that, and quite frankly, this is just easier for me to understand. So you can copy this down. Uh, I might paste in the description, but it's a pretty short function, and you can kind of just yeah, it's not too hard to copy. So I'm going to copy this, and I'm going to paste it into this above the other function. And what this allows me to do is it allows me to just call this function to get a random value between 0 and 1. So I'm going to say, I'm going to create a new variable p. So, and I'm going to make it a double 2. So that's a double, which is a like a double precision something or other. Uh, I'm not entirely sure what it stands for, but you can think of it as a decimal number, or like, yeah, decimal. And this 2 is to say it's like of a size 2, so it has two components to it, like a 2D vector. Double 3 would be a 3D vector. So double 2 equals, or double 2, I'm going to call this p for simplicity, equals random 2, and then this takes as an input a double 2. So I'm going to cast double 2. I'm going to cast the coordinates as a double 2. All right, so that's what this parentheses double 2 does. It takes the stuff inside of these next two, or this next pair of parentheses, and casts it to a two-dimensional double. So I'm going to take the GIDX and the GIDY. And then that should be good. And then the next thing we're going to do is, since this random 2 function only outputs a value of between 0 and 1, and we want, and because each pixel is like just, it's a 1 by 1 thing, and we have like 1,000 pixels per side, we want to take that 0 to 1 range and stretch it out across like 0 to 1,000 on each direction. That way we are covering the whole plane. So we're going to do p times equals this double 2. So casting this to double 2 again. And then I'm going to do res x and res y. So taking the resolution of each thing, and then yeah, what am I saying? Taking the resolution of each axis and then scaling this p value by that amount. Then the next thing we're going to do is we're going to create another variable, and this one time's going to be an integer. We're going to call it sample IDX. And this is essentially going to be the index of the pixel or voxel that we're sampling. And for now, we can just copy this. Except instead of GIDX, we want to use p.x, so the x component of p, and then p.y. And more importantly, these right now, this is just because it's p.x, so it's a single double and this is an integer, so it's going to cause some funny business. So we're going to cast this to an integer, both of these to an integer, although I'll get to p dot y later. And then the next thing that we want to do is we want to clamp it between 0 and the maximum like index per dimension. So because this is 1024 by 1024, the indices for each dimension go between 0 and 1023. So we want to clamp p dot x between 0 and 1023, so we can use a clamp. And 0. And then because we obviously want to be able to scale up this terrain or down, we're going to use the res x. And then we need to minus or subtract 1 from it, because the index of each this is the like total amount of voxels in each direction, and but the index for the voxels starts at 0 instead of 1, so that's why we need to subtract 1. And I'm going to copy this to this side and change the x's to y's. And theoretically, if we replace this sample or this IDX with sample IDX, we should get a bunch of points that are scattered. And boom, voila. So I'm going to make a very minor alteration. So IDX technically doesn't start at 0 for some reason. That's what the stride offset is for, instead of it just being stride x plus stride y. So we are going to, in this if statement, we're going to add in the stride offset. Literally add it in. And we're going to get slightly more dots if you pay attention. So it's going to add about 10% more. Yeah. And essentially this just makes it so that if we want a really small number, it's a little bit more precise. Sorry, there's a plane in the background, so my audio might be picking that up. Next thing I want to do is I want to take this parameter or take this number, and I want to turn it into a proper parameter that we can control. So I'm going to go to this bindings. I'm going to click this green plus, which is going to insert a parameter above this parameter. And the reason being is because you have to add like integer parameters before you add any of these like volume or attributes. There's a bit of a more complicated reason why, but I don't really want to explain that. We can call this num flows or num points. It's much more comprehensible. And then I can add in another input here, which is going to be int num points. A comma after that. Voila. One of the really cool things about doing it this way is that the position of these points will be consistent across resolution. So I'm just going to zoom in here. I want you to track this when I bypass this resample node. This resample node, so this base terrain is a bit higher res. I have this in to make it a little bit more interactive. It's still fast, don't get me wrong. So if I disable this, boom. Actually, that's not a good example because one of the points got like kind of, well, actually, no, it's a fair example. It just turns out these points are like overlapping a little bit. If I pay attention to this one, same position. Super fun. You can see that's it's pretty hard to see, I guess, from out there, but the position of the points do remain relatively consistent. I think, at least. Yeah, it's something like that. I think it's a little bit better on the other one. Um, oh well, I'm not really gonna complain about that. Let's just do another gut check here. Yeah, it's a little bit weird. It's fine on this one. I'm not gonna make a huge fuss about it. You can see they're coming from the same bit. I wonder if I did something differently there or if I'm just seeing things. It's very possible I'm just seeing things. No, I think it's fine. I think there was just a lot of them, so it's getting a little bit messed up. Yeah, like if I zoom in here, this guy is staying in the same place. Okay, I'm not gonna make a big fuss about that. Sorry. Um. Anyways, next step is we need to make these guys actually roll down the hill. So this time, instead of just having these guys basically on their own, just doing it once, we want to add in a for loop um, that will update this p variable a little bit each time. So I'm going to indent these. I'm going to do for int I equals 0. It's less than, let's just start with 100. I plus plus. And close it off. And we're going to see that nothing happens. So in order to make something happen, let's just do p.x plus plus just to increment this x bit of p a little bit each time. And then boom, we have these little stripes. So now we can see these particles are clearly moving and they're writing to a voxel each time. But now we need to get the slope and move them down the slope. And unfortunately, OpenCL doesn't have any like native gradient functions like you might be used to. So we have to kind of build our own. Luckily, it's only a few lines of code. Yeah, it's not too intimidating. The gradient is basically just the slope, like the two-dimensional slope of a point. Yeah, that's all it is. If I want to grab the slope of something here, then and specifically the slope and the direction of the slope, that's what the gradient does. So let's get started with that. The way we compute the gradient is we take, I'm going to first actually delete this. We basically sample, let's say we want to find the gradient of this red point, or the gradient at this red point. We sample the four surrounding, like neighboring points, and we use those and specifically the differences between them to compute the slope. So let's start by just sampling these neighboring points. And so we have four neighbors. Oops. I just did something. What the heck is going on? Okay. So we're going to do another for loop. And we have four neighbors. So let's say int j equals 0. J is less than 4. And then j plus plus. And there are a couple ways we can do this. Either like A, you can figure out how to use like imaginary numbers because those work well with rotations. A little bit more of like the, I guess, intuitive way that I'm going to do it here is not as fast, but it's a little bit easier to digest for folks who don't have a lot of like experience with imaginary numbers. Um, Or you could just do it manually, like for every point, just create a new sample IDX and then figure out how to do that. And it's really not that bad, but uh, yeah, I'm certain there are easier ways to do it than what I do. I'm really queasy about sampling stuff outside of these bounds because historically it's been very finicky and it's like crashed my graphics drivers. I really don't want to do that, so I'm just gonna do the tried and true method here, even if it's not super fast. So we're gonna start by uh, using or creating a new variable. It's also gonna be a double two, grad for gradient. It's gonna be 0. So let's sample these points around it. And just to validate that we're sampling the correct points, I'm going to put this, I'm going to copy this into here. And I'm going to copy this sample IDX into here as well. I'm going to rename it int grad sample IDX. Grad sample IDX. So remember, this value right here, this is our x coordinate. And this value right here, this is our y coordinate. So if I say I want to add 1 to this, it's going to create it's going to sample the point next to it. And vice versa with like minus. All right. So that's how we're going to increment this. So this time we're going to be using some trigonometric functions. This is fun. So we want cosine on our x and then sine on our y. And this will basically just sort of rotate our sample point around this center point. I know it's kind of a weird way of doing it, but it does actually work. So cosine of j and then sine of j. But obviously sine, if you know anything about sine, base like full revolution is 2 pi and j only goes up to 4. So we need to multiply j. So we're going to first cast it to a float because right now it's an integer. Float j times 3.14159 and add an f to signify that this is a float. Then we're going to divide by 2. 2.0 f to be specific. And we're going to cast this cosine function back to an integer so it works within this clamp. And we can just copy this over to the y. Change this from cosine to sine. And then boom, sampling each surrounding neighbor. Next thing we need to do is we need to use this to actually compute the gradient. So we're going to say grad plus equals height of grad sample IDX times a double 2 of our cosine and sine values. If you know the formula for like a gradient is basically or let's just say a derivative. Derivative is a dy over dx, right? So this height, yeah, we're essentially doing, shoot, how do I even, sorry, this is quite hard to explain. just give me a second. We're essentially doing dy over dx here. So height of grad sample idx. Actually, let's make this a little bit more easy to read. So say double dy equals height. Actually, we need to double 2 dy. So this is our gradient formula, right? It's dy over dx. So we need double 2 dy and then double 2 dx. Dy is basically going to just be the difference in our height field across our sample positions. Double 2 dy equals height of grad sample idx minus height of sample idx. And then dx is going to be basically the distance from these sample positions to the center. So, and then that's because it's a double 2, we're sampling in 2 dimensions, right? So it is going to be double 2 of, oh, I forgot. Dude, I am so bad at this. Dx and dy are already these input variables. I completely forgot about that. Let's just call this voxel size x. It's probably a little bit easier anyway. I'm really sorry. So the double 2 of voxel size x and voxel size y. And then because the difference in the, oops, oh man. Okay, just missing a semicolon. The difference between these, because we're computing, that we're sampling every point around this. So we're going to be comparing like this point to this opposite point and this point to this opposite point. It's actually two voxels away. So we need, this is just giving us the size of 1 voxel. So we need to multiply it by 2 to get the size of 2 voxels. So that's going to be our dx. And our dy, we have this difference in height. But we need to add in a separate term, which is just going to be this how should I explain this? Basically, when we want to compute the direction in this way, where we only want to really care about these 2 voxels, right? Because these ones are kind of irrelevant. So we need to scale these bits down to 0 when we want to compute the direction in this way, and then vice versa when we want to compute the direction in this way, or the slope in this way. So we need to add in a separate term here. It's also going to be a double 2. And multiply that. And then this double 2 is essentially just going to be the direction that we're stepping in. So we can copy this direction from our like step increment here. So that's going to be for the X. And we need to do the same thing for the Y. Remember, all that's different between here is the cosine turns into a sine. And that should be good. So I'm going to disable this mask here. And then we can use this gradient to update our position. But in order to do that, I'm going to first add in a variable called v, which is also going to be a double 2. V equals 0. And then p plus equals v. And then v plus equals, or minus equals grad. And I'm going to add in another term here, which is going to be v times equals, let's say 1.0 minus, I'm going to create a variable friction. And it's going to error out when I click out here, but let's add this in. Well, friction and bindings, we add in a friction here. And then voila, you can see interesting things are happening. So this is creating a very sparsely populated trail, but we can see it's actually doing something, which is really fun. Let's go back to 100. The way that we want to get a smooth line here instead of a this spotty bit is we need to add in another. We can't be moving by more than one voxel for each step. So in order to do that, you can either do this normalized function for v, which is basically going to make sure v always has a length of 1, and that does work. But it can get a little bit sketchy on flat surfaces, so if I change the size of this mountain down a bit. Actually, it's behaving pretty well. Yeah, it's fine. It works. Anyways, now we have a very nice thing. The next thing that I generally do sometimes is instead of normalize v, I add a little bit of a slight dampening component to it. So it's v over parentheses length v plus some small component like 0.001. And this functionally does the same thing, but it makes sure that the really small values of v aren't like shooting off because of some arbitrarily small, could even be like imprecision error. And then the next thing I'm going to do is instead of just setting this equal to 1, I'm going to say this increments by 1. More precisely, increments by a value that I'm going to call the flow strength. And then we can add that in here as well. Float. I got a new keyboard and it's messing up my typing. Then add another binding here. So flow strength. And then it's going to be a float. You see, there we go. And if I change this to this higher number, we can see how that's working in our favor here. And because we're getting a ton of these little tiny dots over here, I'm going to add in another term at the end of this. call this times length of b. And that's going to eliminate a lot of the really tiny bits that shouldn't really be shown up. And you can see with our friction, can change everything about that, which is really fun. But one of the things that I am kind of noticing is that we have a lot of these little bits that are cutting off at the end here. And that's kind of unfortunate because it's just kind of jarring. So instead of just limiting this to 100 iterations, I'm going to say we want the max number of iterations here to be equal to the largest dimension in this grid, right? That way, if it needs to go all the way across the grid, it can. So I'm going to say it's going to be the maximum of res x and res y. And boom, now we have a ton of these little hairs shooting off. And it might be a little bit much, but it works. Turn friction down a little bit. Let's package this into a proper HDA like this. That way we can have direct access to these parameters without having to go into the node. So I'm going to assets, a new digital asset from selection. I'm just going to call this tutorial flow lines. And then I can click create. I'm going to create 3 parameters inside of this window. One is going to be a logarithmic integer, and I'm going to call this one num flows. I'm going to set the default to 1,000 and the range from 1 to 1,000,000. Actually, yeah, 10,000 probably. Let's see. Yeah, that's good. The next one will be the friction, which I also want to be a logarithmic float this time. Set it to be like 0.05, 0.01 to 1, I think is good. 0.01 plus friction. And then finally, I want that flow strength. There's another logarithmic float. Flow strength. Let's change this all the way down to 0.0, just 0. And the default's gonna be like 0.0. All right. So the first one, I'm going to copy parameter here, and then paste it into here. Paste relative references. Copy parameter. Paste relative references. Then copy parameter. And paste relative references. Let's go back to this. So now these are linked up. Yeah, fun stuff. One thing that I'm not too fond of is with this friction, it's getting so much like darker. So much more stuff is happening when it goes to low values. So I'm just going to add in a clamp to this this value right here. I'm just going to say min of 1.0 and this length. It's going to make sure it doesn't explode into weird values. so it looks a little bit more cohesive. So yeah, it's really fun. I like it. Let's go into here and let's eliminate the stray underscore. Then when we click apply, it's going to save a new version. You can also just click save node type. Match current definition if you want to remove this little red bit, which can be irritating to look at. And here's what it looks like at higher resolutions. Pretty cool. I think it's necessary to one of the things that kind of just saw here is that the behavior gets a little bit different when changing resolutions. It looks as if like this is much more contained. So one of the ways that we can do that is by adding another term to this bit, which is going to be the power function. Essentially, we can just take the length of the x. No, we can't do that. Sorry. Grab the voxel size x and plug that into the second term. Oh, we need to make this a double. Yeah, so that's a lot closer to the original. And save node type. Match current definition. Then you can add a few more flows to make it brighter. Yeah, so that's really fun. So that's about it. Hopefully you guys enjoyed. I know it was kind of an unedited mess in some places, but I thought this turned out all right. I thought it was a pretty interesting little study to do. And yeah, hopefully this was useful to you. Check out the Discord server in the description. There's been a lot of work there that I've done with this whole terrain tool set that I've been building in Houdini. And I've been, it's basically been my devlog for that, which has been fun. So you can see more info about that. Yeah. Hopefully you guys enjoyed and have a good one. Bye.